This is Regenerative Skills, the podcast helping you to learn the skills and solutions to create an abundant and connected future. I'm your host, Oliver Gaucher. So at this point, I think we all know that YouTube videos, social media posts, and blog snippets will only get you so far. If you really want to develop the knowledge and skills you need to live regeneratively, you need the thorough information in a full book. Through their diverse range of publications, New Society Publishers' books explore topics that are at the forefront of creating positive change in our world. From regenerative agriculture and permaculture to social justice and eco-conscious living, their books cover a wide spectrum of subjects that empower readers to lead more regenerative and fulfilling lives. So whether you're a seasoned environmentalist, a curious beginner, or someone simply seeking inspiration and guidance on your journey towards regenerative living, New Society Publishers is here to support you every step of the way. If you subscribe right now to their newsletter at newsociety.com, you'll be the first to receive sneak peeks at new content and get discounts on upcoming title releases. You'll even get an exclusive discount code on their first purchase of books, ebooks, or audiobooks. So sign up today at newsociety.com. So I had done one other episode in the past on this topic of floating wetlands that I'd like to revisit today as we continue with this series on regenerative water solutions. In today's episode, I got to speak with Bruce Kania of Floating Island International, which developed their patented Biohaven floating island technology as a solution to algae-ridden and nutrient-impaired waterways since 2005. And since then, they've launched over 9,000 island systems worldwide as solutions to a variety of problems facing contaminated water. In this interview, Bruce breaks down the chemical and biological processes that happen in the water when there's heavy nutrient load, and how it affects the balance of oxygen and the life forms that depend on it. He also tells me how the floating islands that he's helped to develop work to cycle nutrients of polluted waterways back into the food web that then fosters the beneficial life forms that are emergent elements of healthy water ecosystems and that mature to help the whole system and surrounding ecology to thrive. We also take a look at a case study of Fish Fry Lake in Montana, and how it's gone from a polluted lake with regular algae blooms to become the most productive wild fishery in Montana, where people can even swim and snorkel. So be sure to stick around to the end of the interview as Bruce explains just how big the potential for these floating wetland systems is, as he's looking to develop inhabited floating islands that help to filter and clean the great plastic garbage patches in the Pacific Ocean, and the possibility of creating floating solar farms that function as new real estate as well. Bruce also mentions a couple of opportunities for jobs and internships if this is the type of project that you want to get involved in. There's an incredible amount of hope and inspiration in this episode, so get ready to learn and dream as I hand things over now to Bruce.
Why don't I start with a quick overview of the event, I guess, that inspired me to look into potential ways to fix water. In fact, here at Shepherd, our research center is a place that had been a sugar beet farm. It's right along the river, the Yellowstone River. And in fact, it's right at the point on the map where the Yellowstone, which has been flowing north out of Yellowstone Park, makes a definitive turn to the east. So you can see the location from space very, very readily. But I had purchased a property with a view to develop innovation as it related to the intersection between agriculture and wildlife. That I'd been an inventor and focused on a licensing strategy where I would develop inventions and license them to companies that could commercialize them. And I had a passion around wildlife in particular, but certainly from my personal experience growing up with relatives who farmed and helping them occasionally on the farm, that intersection, it became really apparent. It has been apparent to me that agriculture is a massive impact on wildlife, and figuring out how those two could correspond well. At the time, most inventors were really focused on the IT revolution, And so as sort of a contrarian by nature, I was going off on a different tangent. But when originally essentially developing this research center, I built a pond, and the pond was receiving irrigation ditch water, which is the way in which agriculture happens in this part of the world. You need to essentially step up from the shortgrass prairie uh, situation where essentially between anywhere from 6 to 12 or 13 inches of moisture per year is typical in this country without irrigation. So just one notch up from desert. But this pond received water from the bench ditch here in this region, and I had a black dog that would swim in the pond. And on occasion, toward late summer, we noted something really distinct. He would come out of the pond and his coat would take on a reddish hue. The dog was particularly smelly. You could smell him from 50 feet away. And it was amazing to me. I'm thinking to myself, here's the Yellowstone River. We're very near the headwaters of the Yellowstone River. And something's in this water that is influencing the dog's hair. And it's incredibly potent. The dog would actually take on this red hue and stink. And that motivated me to connect with contacts of mine at Montana State University Center for Biofilm Engineering, folks that understand water quality issues. They explained that we were experiencing cyanobacteria. And cyanobacteria was essentially the problem that was going on that was causing the dog's hair to take on that reddish hue. But it became a concern of mine of how, what's really happening with water and agriculture. And that became a similar focus. Instead of just the intersection of wildlife and agriculture, I determined I'd focus down on water and agriculture. And that became essentially the driver that led me to look at potential ways around nature as model that would allow us to fix water. So biomimicry, or nature as model, became the driving theme behind what we do here.
And with these observable issues in the water, how did you start to understand the roots of the problem and start to come to some conclusions about how you could intervene to improve not only the health of the water itself, but the whole system that was causing this problem?
The data that has been generated by the Center for Biofilm Engineering, one of just a couple premier research centers that focus down on which is microbes and their residue, which is one of the two engines of life. One engine of life would be the autotrophic, plant material that essentially uses solar energy to digest minerals and grow plant material. The other engine of life being the heterotrophic form of life. The microbes and the residue kind of launch that one. And they are the organisms, like human beings, that eat organic material and derive our energy from that. So the two engines of life, the heterotrophic is usually underemphasized when it comes to stewardship of water. I've learned that since 2005 when that red dog event actually happened. But the idea of managing a waterway, for example, around both of those engines of life, that became the driving mission. And looking at nature and natural methods to find ways that nature is modeling that is what led us ultimately to naturally occurring peat-based floating islands. They occur literally around the planet. And here in Montana, we're around the 45th parallel, and they're not infrequent. They happen occasionally throughout the continent and south, in fact, in the southern hemisphere as well. But these peat-based floating islands essentially are a mechanism by which nature is creating real estate. And we've studied the phenomenon. We're trying to essentially replicate or biomimic this phenomenon. And to give you an example, Oliver, we We have at one point, we launched an island. We knew what its dry weight was very clearly upon launch. And then after 11 weeks of growing season, we brought the island back out again, went back to air dry and tested for biomass buildup and learned that we had grown by 72%. That growth took two forms primarily. One form was the biofilm and the TSS, the total suspended solids, the particulates in water, the dust in water that bonds to that biofilm. That was one of the forms. The other form would be plant humus that occurs on top of the island and builds up. So the island was getting progressively thicker over time, almost doubling in about 2/3 of one growing season. When we study naturally occurring islands, Oliver, like in a place, for example, called Chippewa Flowage in northern Wisconsin, where the Chippewa River was dammed at one point, water backs up over peat bogs which incorporate there's such a fine density of material in the peat itself that the biogas generated by microbes in the peat is trapped, making that peat somewhat buoyant. So when water backs up over the peat bog, a fraction of the peat can rip up and become a floating island, after which plants colonize that. And as the island gets progressively thicker, the islands grow. One island that we study a lot is actually 30 acres large and supports tens of thousands of mature white cedar trees and other forms of trees too. But the biocomplexity associated with the riparian edge around the perimeter of that island is incredible. There's so many things we've learned from these islands that stand out. Here's another example. You take a 1 square meter section around the perimeter of the island and count the species of plants that occur there. We have, in one instance, we came up with nearly 200. But over and above that, the other stark difference, in a setting like that as compared to human agriculture, for example, is that you don't find annuals occurring in that setting. It's almost entirely perennial plant life. Annuals are I almost consider annuals to be a human invention in terms of how we focus on them with agriculture. But nature is focusing on perennials that invest a lot more in their root systems and are typically more resilient too. So the island itself, that 30-acre island, within about 90 feet of its perimeter, was 19 feet thick and essentially moves around the Chippewa flowage. But the other point about Chippewa flowage that is reflective of the impact these floating islands can have is the fact that the apex predator fish in North America, arguably would be the muskellunge that's in the pike family, but bigger than northern pike. In fact, the world record came from that flowage at 69 pounds, 15 ounces. And when you snorkel or dive around the perimeter of this island, it becomes very apparent why. The islands are fish aggregating devices, which is a term that's used around aquaculture. And in particular, I've run across that term in reference to brush park aquaculture, which has some parallels with the floating island system that we're studying here. But in any case, the matrix of roots around the perimeter of the island were functioning as biofilm reactive surface area. And growing biofilm, which is the base material for periphyton. Periphyton is biofilm and whatever sticks to it. And when biofilm occurs near the surface, there'll be a phytoplankton component of it. It could be a green algae, or it could be even a blue-green, perhaps even some cyanobacteria. But as you get lower in the water and light becomes less available, then another form of phytoplankton, the diatoms, tend to be the dominant form of autotrophic life that combines with the biofilm/periphyton. And the reality here is that diatom-based periphyton is the incredible way to grow fish. It cycles into fish very readily. So bear in mind, if you have both autotrophic and heterotrophic going on in a waterway, you're cycling nutrients out of that water and up and into the food web at a terrific rate. And the productivity that can be associated with that when dealing with nutrient impaired water, with water that has simply too many nutrients because of agriculture, is startling. It's remarkable and very, very exciting to me. We're seeing that phenomenon occur now on Fish Fry Lake here in Montana, which I can arguably say is the most productive wild fishery in the state of Montana. The catch rate on fish is literally 1 fish a minute. And those fish represent a terrific way to cycle nutrients out of the water and ultimately prevent harmful algae blooms that tend to occur otherwise.
It seems like a simple way of explaining it or kind of distilling it down is that these nutrients are only becoming an issue because they're out of balance with the rest of the system and because some part of it has been impaired either by removing elements that function like swamps or wetlands that are natural filtration systems that would do this, regularly, and putting in some kind of intermediary in order to bring the nutrients back into the food web and convert them into things that are beneficial for the entire system. In your case, fish, plant matter, and whatnot. Because, essentially they are nutrients, and if managed correctly, they can be a beneficial, accelerator for other forms of life in the system that you're trying to foster. But before we talk more about the larger aspect of bringing all of these essential components of an ecosystem into harmonic function, can you tell me a little bit more about the function of biofilm in water filtration and how exactly it does that?
Biofilm, Oliver, is limited by the usual parameters, but the two really big ones are surface area and circulation. Temperature, residence time, pH of the water, all those are other factors, but the two big ones are surface area and circulation. So those plant roots that occurred around the perimeter of the floating island that we study represent a blend, a wonderful setting in which both occur. The surface area is the plant roots themselves and the root hairs on those plant roots. And over and above that, the wind and wave action that influences or comes in contact with that surface area represents a form of circulation. The phytoplankton component is how oxygen is, and dissolved oxygen is being communicated back into the water, by the way. But diatoms, unlike cyanobacteria or blue-green algae, they have a different life model. They don't go through that remarkable feast or famine growth, explosive growth, and then die off, and then consumption of dissolved oxygen that the blue-greens and the cyanobacteria go through. So diatoms are more of a steady state. Then a gentleman, Redfield, developed at one point, traveled around the world and attempted to answer this question: what is the ratio of nutrient that is essentially nature's model? What is the ratio that occurs in living cells all over the ocean? And he came back with these numbers: 106 carbon, 16 nitrogen, 1 phosphorus. But when you take those numbers and compare them to the fertilizer mix ratio that soil scientists and agriculture essentially has been employing, you'll see, for example, 30-30-10. Equal parts: 1 part nitrogen, 1 part phosphorus, and then some potassium. And then they lead carbon to the soil. Now, you don't necessarily have to add that. It's already there. It's ubiquitous. But agriculture is operating well outside of nature's model. And when those fertilizers are applied to land and ultimately a water event happens, that same ratio ends up getting flushed occasionally into water, water being at the bottom of a watershed, and that's where it collects and accumulates. And that particular phenomenon is why today we're experiencing explosive new volumes of harmful algae blooms. The numbers relative to the U.S. and harmful algae blooms, where they're occurring, and the impact of them. There's two particular impacts associated with harmful algae blooms. One is that the explosive growth ultimately becomes massive volume of the plant material itself, which when it dies and is biologically broke down, consumes, the biological oxygen demand associated with that, pulls huge volumes of dissolved oxygen out of the water and can actually de-aerate and literally make life for air-breathing biota, for dissolved oxygen-breathing biota in the water, impossible. They die. The other thing that harmful algae blooms occasionally do, not all the time, but when stressed, they occasionally can generate a form of microcystin that is toxic. And that can introduce another very critical variable to a waterway, making the water dangerous for livestock or even for people to experience and or pets. But that's happening with increasing frequency around the U.S. It's happening, note though, however, this is happening in the developed world where fertilizer, where orthophosphate, synthetic phosphorus essentially derived from hydrocarbons, when that essentially occurs in a waterway in big volumes, it typically is in freshwater, it typically is the critical variable that results in the harmful algae. Nitrogen can play a role too.
Yeah, I've actually seen examples of this all over the world. Where I used to live in Lake Atitlan in Guatemala, there were constantly different initiatives trying to work on cleaning up the lake there, which suffered from algae blooms and cyanobacteria in different seasons and after different weather events, often contributed by the agriculture going on around, but also just untreated sewage from the towns that were, expanding super fast around there. And you're from Wisconsin. I lived there for a while, and Lake Menominee, where I used to live not too far from the Twin Cities, was in late summer often had like this layer of this pea soup, that blue-green algae that just suffocated that place and made it really unpleasant, changed the odor. And yeah, like you said, like it's happening in developed countries, which actually to me doesn't surprise me that much, because it's where we're consuming so many of these chemicals in our agricultural systems. But I've seen it, in what we might call undeveloped countries, which don't seem to be sort of under the control of as much agribusiness and harmful chemicals, but it is really starting to get into all of our water systems. And I'd like to hear from your experience about some of the importance of the circulation and oxygenation for healthy water, and how this plays in with the systems, especially the floating streambed systems that you implement.
Oliver, we've searched for cost-effective means by which to incorporate that blend that we describe as nature's wetland effect, that blend of surface area and circulation, and from that derived an air-driven floating streambed effect that continues to evolve. Today, there's a nanobubble, phenomenon that is being developed that literally could provide another major means by which to further enhance for appropriate dissolved oxygen content or concentration in waterways, because these nanobubble systems are unique in that there's something about them that makes the nanobubble neutral buoyant. So instead of an air bubble that wants to rise immediately to the surface, these nanobubbles will remain within the water table. In fact, some will even penetrate into the benthic zone, into the sludge, the mud on the bottom of a waterway, and begin the process of aerating that. So the idea of enhanced circulation, aeration, using perhaps air-driven water movement like we do with the floating stream bed, or perhaps integrating nano-bubbler systems with that, and doing so on an off-grid basis. In other words, using solar power to drive that. That's the direction we're taking now. We're looking at massive solar Biohaven projects that can actually represent an answer to the scalability issue connected with fixing some of the incredibly nutrient impaired waterways around the world. Just think of Lake Erie, or think of Chesapeake Bay, or think even of the incredible dead zone that occurs in the Gulf of Mexico. I know we've all heard of that one, but there's another 390 plus dead zones occurring in marine conditions, always as a result of the nutrients that are cycling into the ocean at collection points at the bottom of watersheds. Rivers that cycle nutrients into the ocean, and massive algae blooms that occur in conjunction with them. And it's not just the blue-green and cyanobacteria we're talking about. It can be red algae. And you've probably heard of the toxicity associated with red algae that occurs in different marine settings. It can very much influence the safety of consuming shellfish, for example. But the idea here that there's a means by which to intercept those nutrients and cycle them into appropriate, and that's not a fair word, but cycle them into desirable biota, like, for example, healthy, colorful, vibrant fish. I'm inspired actually by the test pond that we have here at Shepherd. It's a small lake, only 6.5 acres of surface area, but roughly 54 acre feet of water. An acre foot is essentially an acre, 12 inches deep. So that fish fry lake system, when we started, we initially took a swale that had a seasonal pond. We dug it out, we dammed it, and it became essentially a perennial pond. And immediately, within days, essentially developed a complete cover of filamentous algae and cyanobacteria. You couldn't see open water. Today, the lake isn't just free of the harmful algae bloom, but you've got water clarity that can extend as far as 19 feet. And beyond that, it's an incredible fishery. And the fish are extremely healthy. We can essentially propagate enhanced fishery in that lake by providing additional habitat. And today it's got an incredible forage base. The fathead minnow, the crawfish, the other forms of forage fish that occur here ultimately move up and into and through the food web. And we end up harvesting at the rate of about 25, 27 pounds of fish per acre foot of water per year. And we're just keeping up with the inflow phosphorus when we do that. We're just keeping up with it. We're not really addressing what's called the legacy phosphorus unless we further expand our harvest from that waterway. But in the face of the COVID-19 and what's going on today, we're noting that many, many people are looking at water that they're stewarding, and they're thinking about what can they do to help fix that water. So we're seeing a wonderful private water initiative unfolding here in the U.S. that will hopefully keep happening as the pandemic transitions.
Well, so let's use this as a deeper case study, that of Fish Fry Lake, and you explained how you made some alterations in the landscape for it to be able to hold water, and that immediately upon filling up and getting established, it developed those cyanobacteria and algae problems right from the start because it's gaining most of its water from agricultural runoff in the region, if I understood correctly. Can you tell me about how you went from that stage to the interventions, how, first of all, how you came up with them, the interventions that you put in that helped you get to this place now with the incredible turnaround of the quality of water and the productivity of the site that you now enjoy.
The reality, Oliver, is that I've had a lot of wonderful scientists essentially looking over my shoulder as we've engaged in this experiment. People like Dr. Al Cunningham, one of the initial co-founders of the Center for Biohaven Engineering, an engineer named Frank Stewart, who isn't part of the CD, the essentially Center for Biohaven Engineering, but is sort of a liaison between them and me. He's a civil engineer. Dr. Mark Meinzel, and Mark graduated from the center, but Mark is also a biohaven engineer. And with these folks helping, we've been able to structure, test, and move forward scientifically around the process of understanding how much surface area and circulation we will need or is needed in Fish Fry Lake to achieve what we do there. So the islands themselves and the surface area, every cubic foot of Biohaven floating island provides 375 square feet of surface area. And when we filter through that, we have that very effective bioreactive surface area in which we can cycle nutrients even more aggressively than blue-green algae can into biofilm. So we're working around that same premise. We want both the autotrophic life forms and the heterotrophic life forms, both engines of life we're employing to handle the nutrient load in Fish Fry Lake. But here's the key point, and I really want to emphasize this, Oliver, which is that large waterways, like Lake Erie, that experience massive algae blooms today, the only way we're going to be able to replicate what's happening on a place like Fish Fry Lake, which is so much smaller, is by making the systems that are there to fix the lake commercially viable. The idea of using Biohaven and its biofilm reactive surface area matrix to essentially float photovoltaic farms, solar energy farms that will generate alternative energy, clean alternative energy, and can be built to scale, are a way to actually begin to attack the fix-up of these massive waterways, whether it be Lake Erie or Lake Okeechobee or Lake Mead or the Las Vegas Wash or the Chesapeake Bay. There are so many in just New York State, for example. In 2018, there were 394 reported harmful algae blooms, and many of them occurring in some very large lakes. So you can appreciate the scale of the challenge, but in some perspectives, it actually is a window of opportunity for humanity. If we do essentially learn how to cycle those nutrients into desired biota, into appropriate life forms to essentially perennialize those waterways, take them away from the annuals, if you will, the cyanobacteria effect, the resulting, heaven on earth, and the incredible productivity and health of the waterway. The idea of taking a Fish Fry Lake and using it as an initial model. We focused on floating islands, but there have been other ideas that have been employed there. For example, we have a crawfish incubator design in which we use a net bag full of the inert matrix that doesn't break down. It's made of a recycled plastic that is further armored, so it doesn't break down. And we suspend that vertically in a waterway that's essentially colonized by crawfish, and they can use it as a ladder to move up or down. So if dissolved oxygen becomes problematic at depth, they can move up and do so without essentially being suffocated. The nano bubbler system that we're talking about, we are installing one of them in Fish Fry Lake too, and on that basis, We can make the lake productive from top to bottom. Its deepest point, 28 feet, instead of being anoxic, can now be aerobic. There's a key point about this too that not many people today are aware of, and that is that the lakes across not North America, because I don't know, I don't have good data for Canada, but I can say lakes across the United States, over half of them are nutrient impaired. And when they're nutrient impaired, they develop an anoxic layer of water. That means water without breathable oxygen in it. And that anoxic water generates a different form of greenhouse gas, methane and nitrous oxide, instead of CO2. Accordingly, because of that much more potent greenhouse gas, these lakes across the U.S. are greenhouse gas factories. And unless we fix them, they're going to continue contributing to climate change. So the pressure's on to actually find ways to make the potential to fix these massive waterways, and the small ones too, and transition them back to health in order to have take measures around reduction of these greenhouse gas factories.
I find that really inspiring, and I really want to come back to the full potential of the implication of these systems, both for the ecosystem and economically. But I still have some things that I'm trying to work out about this case study of Fish Fry Lake. Now, you mentioned that right now you're using the inflow of phosphorus and cycling it back into the food web as the primary sort of propellant for the amount of fish that you're able to produce. If for some reason the pollution coming from the agricultural runoff was not bringing in the same amount of nutrients from other sources, would you then have to consider putting in either fish feed or other sort of nutrient source in order to maintain the stock rates that you have? Or is it independent of what's coming in?
In fact, a scientist from the NIWA out of New Zealand at one point mentioned a large waterway in New Zealand and noted to me that even if all of the inflow of phosphorus stopped completely, they had estimated that there would be an overage, they wouldn't catch up relative to having a balanced phosphorus ratio happening in the water for at least 4 decades.
Oh, wow. Okay. So the accumulation is so large that you're not even getting to the point where you're diminishing the stored phosphorus in the land, or like that's gone into the lower layers. You're just because I do remember you mentioning this, are just kind of breaking even with the amount that's coming in and cycling that through.
Correct. And then the legacy nutrient inventory still ultimately represents a recoverable resource.
Mm-hmm.
And here's the other point. Here we are in Chippewa flowage, which is in the northern woods of northern Wisconsin, minimal agriculture influx. And it is super abundant, even based on nature's standard ratio. It's a premier fishery. It's a place where world record fish are like the muskie, come from. So once we accept that nature's wetland effect is how you fix water, and we start employing that in these nutrient-rich waterways that typically happen where humans happen, agriculture takes place. Agriculture being responsible for some 80 to 85% of the nutrient inflow. But other forms of pollution like wastewater or stormwater also can influence these waterways and will continue to do so over time. But as we gain motivation and ability to employ and leverage nature's wetland effect, we're going to turn these nutrient-rich waterways that are today the harmful algae bloom susceptible waterways into remarkable places, wonderful places where incredible abundance will occur. And we're seeing that here on Fish Fry Lake, and it's truly energizing to be around. I did a TED Talk a few years ago, and I tried to describe the incredible hope and prospect associated with this phenomenon of taking and essentially learning how to collaborate with nature and move into an upward spiral with our water instead of a downward spiral. Today, for example, Oliver, if you look underneath islands on Fish Fry Lake, you're likely to find freshwater sponge that has colonized the island matrix. And it's a filter feeder. It's natural, it's native, it got here by itself. It's like nature's on our side.
Mm-hmm.
And that freshwater sponge is being grazed by red ear sunfish. And they can graze on a portion of it that protrudes from the matrix, but the balance of that sponge occurs within the matrix and actually grows around it. So it has a security zone too, and it's never overly grazed. In any case, we're seeing that nature is extremely available, willing. We give it the window of opportunity, there it is. And in the process, the TSS in that water, which will contain everything, the nutrients, the carbon, the other forms of contaminant, the dust essentially, that essentially represents everything that washed into the waterway, including microplastics, by the way. Here, the sticky biofilm bonds all of that onto it, and it becomes a form of paraphyte to be biosequestered, to essentially be processed into real estate. That's a way of looking at it. The islands, as they grow and develop and essentially get thicker and ultimately will frequently tie into a shoreline, for example, and become part of an overhanging bank effect, wonderful riparian edge habitat. What we're seeing is, could we do that purposely? Could we do that large enough scale to actually go after the gyres of plastic that occur in the oceans? I'm envisioning that happening one day, and it really is. It's part of the energization, I guess, effect that I mentioned earlier.
No, it's easy to see, and it's something that I got from listening to your previous interviews and looking into some of this work. And I've been in contact with a number of other companies and individuals who are working on these types of floating wetland systems. With that said, can you explain the technology and the components that make up your floating islands? And yeah, if this is something that needs to be made in an industrial setting, or is this something that people can manufacture for themselves?
Well, today there's about 9,000 biohavens launched around the world. We have half a dozen licensed manufacturers building islands in New Zealand, in the Netherlands, in China, and several here in the U.S. But the islands are made of an inert form of plastic, recycled plastic, polyester. That's what drinking water bottles are made of. It's fabricated into a non-woven matrix, like a filter-like material. And then it's armored. Our design life on today's biohavens, Oliver, is 60 years. What we're really saying when we say that is the islands are indefinite. They're like a seed. Their durability, essentially, the island will become encased in humus. As it gets progressively thicker, the matrix is totally covered and encased within organic material, mostly organic material. TSS, of course, can have a variable, which is what we're pulling from, can have a variable consistency. Typically in many waterways, it'll range anywhere from 90% organic, like in Chippewa flowage, to perhaps 50% here with our ditch water, where the other fraction might be clay colloidals or something inert like that, the big fractions at least. But this polyester, which is one of the very safest forms of polymer, which is why it's used in drinking water bottles, is further armored with a coating of the same kind of liner material that's used to coat the insides of municipal drinking water containers, massive tanks.
Mm-hmm.
And it's also the same material used to coat the bedding of pickup trucks. And it's incredibly UV resistant. So your question about can people build floating islands at home? I went through somewhere between 600 and 1,000 prototypes before we got Biohaven to the point where we thought it was commercial, and we launched. And since then, we've continued to improve and develop around it. And there are folks, or in fact, we know of some settings where people have developed their own islands, and there's been a lot of creative things happening around that. But I want to emphasize that if they do this, if they do want to build their own island, that use nature as model. Note that those floating peat bogs that occur in places like Chippewa Flowage or Floating Island Lake in Yellowstone Park, but they represent the model. And if somebody wants to build a floating island, they should do some diligence and track down how nature does it. I'll note one other thing. When we build the islands, Oliver, we do inject a form of marine foam. We inject it into the matrix. And so it forms a nodule of buoyancy that allows us to design for whatever level of what we call reserve buoyancy we need. The reserve buoyancy then allows us to design. Do we need to support 900 tons of gravel for a habitat island for the Caspian Tern for the Army Corps of Engineers? We've done that. Or do we need to support a solar farm? We will do that. We're in fact talking right now with an international alternative energy developer from Europe, and we're essentially testing and working with them around that very prospect. So these are truly exciting times, and I hope I've answered your question in terms of the construction of floating islands and how we do what we do. But I did want to include one other point. Biofilm is buoyant. When you provide sufficient surface area, biofilm, which is ubiquitous underwater, will occur. And when you keep that system aerobic, it will generate 4.5 times or more biogas than it does if and when it slips into anoxic status. What that means is that surface area and circulation, aeration, should come together in your system.
Well, so Bruce, I understand that part, and it was very well answered. But I'm wondering if these islands then get to a point, either in regular decomposition as the carbon material starts to break down, or even just in amount of mass as they grow at the bioaccumulation that you mentioned, that they either need to be harvested out or broken down and replenished, or some other measure taken so that they don't overgrow the space or even potentially start to sink. Is there regular maintenance that needs to be done on these?
You remember that 30-acre island I mentioned in Chippewa Flowage?
Yeah, actually, I had meant to ask you if is that a man-made structure or is that naturally occurring?
Naturally occurring.
Okay.
And the reservoir was only 88 years old. So we projected that island probably occurred with the initial flooding, that backing up of water from the because it's a reservoir that it's probably at the time 88 years old. And so right now, that was some 8 or 9 years ago, so it's even older now. But the point is that 19 feet thick, roughly 30 yards from the edge, shaped like a deep dish pie. Eventually, it'll probably tie into shore and lock in and become part of the waterways shoreline. How long will that last? And the other, this vision, Oliver, of harvesting plastic from the gyres where it accumulates in the Pacific Ocean. The huge component of the plastic in that setting are microplastics. That's the bulk of it. And the idea of incorporating them into the biomass that becomes literally large islands that people live on, I believe that vision will happen. And I don't think we're that far away from being able to do it.
Well, let's continue to explore some of the full potential of this technology because it's not a single technology in and of itself. You're just mimicking these naturally occurring islands and their own growth rates and maturation through a little bit of guidance and a little bit of, I guess, modern technology put in to give it some parameters, it sounds like, more than anything. And in a few cases, some mechanical assistance, like in the case of the nanobubbles or aeration pumps. You mentioned that this has the potential to, be a system that functions with fisheries, much like the lake that you've used as an example, that it has the buoyancy that can hold perhaps settlements, houses, solar farms. Where do you see this going eventually, and where are you trying to direct it with your company?
The idea of being able to grow new real estate has incredible implications. I recently looked at a map of Florida and what happens in Florida as sea level rises. The vision, Oliver, of providing a means by which humans can still live and function in those settings, I think that's in our future. I guess my hope is that I don't. Well, let me say it this way. I believe that here in the United States, the current administration is not being responsive around climate change, and that very much has to change. I think the idea of the world stage collaborating around the response to climate change is fundamental, has to happen. So in answer to your question about the future, I am optimistic, I'm hopeful and optimistic that humans will become responsive and that will take on this challenge internationally and ultimately test the premise and prove it out that we can grow new real estate and live on it. But in the process of doing that, we're also going to clean up our waterways. We're also going to produce the abundant alternative energy that it makes such systems scalable, helps pay for them.
Yeah, it's an important component.
Yeah, we call it going commercial. We have to be commercial with our solutions. Solutions by themselves are simply too expensive.
Yeah, well said, Bruce. And on that note, I know that you have some opportunities for both jobs and internships. For the people listening to this who feel inspired by your vision and the work that you've pioneered in this area, how can they get in touch with you and perhaps investigate further how they can join and help to accelerate this type of work?
Our website, floatingislandinternational.com, info at, the Floating Island International. And we'll get them in touch with our folks. And I can say, too, that interns are a huge part of the energy that happens here. We've had some incredibly wonderful individuals come through here and spend the season with us and then go on to function within the network. And today we truly are an international network. So the window of opportunity around working in this field is a very large one.
It does really seem to be growing and picking up pace, which is great because certainly this type of work is in very dire need at the moment. And your website has a lot of really great resources on there, a number of which I will link to on the show notes for this episode, including the TED Talk that you did, which you mentioned. You have a great article that really taught me a few things, the do's and don'ts of waterway stewardship. And the link for those internship opportunities is there as well that I'll be sure to link to.
Great. Well, Oliver, thank you very much for the work you're doing too. Yeah, I'm so grateful to you and to people like you that have leveraged the current wonderful abilities to communicate across the planet. So thank you for what you do too. And I very much appreciate your invitation to present here today.
It's been absolutely my pleasure. I appreciate your support, and I really look forward to staying in contact. It seems like you're on a very positive trajectory that is accelerating, especially with the gain of support and the urgency that's come out of the coronavirus crisis, and people being much more aware in just a short time of how closely linked environmental problems and catastrophes in our ecosystems come to affect us, and realizing that it's not separate, that our actions are directly linked to the health and the comfort of our own lives. And so thank you so much for your work. I look forward to being in touch again in the future, and you have a great rest of your day.
You too. Thank you, Oliver.
Now, before we wrap this up, just remember that these episodes are only the beginning of the learning resources, design and coaching services, in-person courses, and interactive community that are available through Regenerative Skills. The Discord server is our free community where you can connect with other like-minded listeners, exchange ideas, stories, tips, and resources, as well as interact with me directly and quite a few former guests from this show. Our Instagram account @regen_skills is the best place to see the projects that me and the team are working on, both for clients and collaborators, as well as on our own properties. I'll also be announcing the certification courses, workshops, and gatherings that we've got coming up later this year. If you're interested in getting dedicated support for your own project, you can now schedule a free planning session with one of our team members through the request form on our website. You can also find all the links, show notes, and past resources there at regenerativeskills.com. We truly believe that no matter your experience, your knowledge, abilities, resources, or background, you can be a powerful force for regeneration on this planet, and we're here to help you find your path. So as always, remember to keep taking those little steps every day towards a regenerative future, and I'll be right by your side along the way.